Hello students, in this video we'll prove the complex spectral theorem. So the complex spectral theorem states the following. It's one of the crown jewels of linear algebra. It says if V is a complex inner product space, and T is a mapping from V into V, then T has an orthonormal basis, then V has an orthonormal basis of eigenvectors of T if and only if T is normal. And recall from previous videos, what's the normal condition? A operator is normal if it commutes with its adjoint, right? If T star T is equal to T star, those are normal operators, right? And of course, the salient feature of normal operators is that this is true if and only if T of any vector V, the length of T of any vector V, is the same as the length of T star V, right? That just follows exactly from the definition of adjoints and using the inner products of these things. So if you square this relationship over here and use duality, you can prove this relationship over here. And that's going to be the fundamental tool in proving this. So let's first suppose. So suppose first, here's our proof of this theorem. Suppose that T has orthonormal eigenvectors. Collection of orthonormal eigenvectors. That span V. Okay. And so list them. You can say phi 1 hat up to phi n hat, where of course the dimension of V here is equal to n, right? And now let's look at the matrix representation of T with respect to this basis. So the matrix of T with respect to the basis phi 1 hat, phi n hat is just going to be a diagonal matrix, right? And it's going to be diagonal lambda 1 through lambda n, right? And therefore, what will the matrix of T star be, which is the conjugate transpose, right? So the matrix of T star, with respect to this basis, we know that those are also eigenvectors for T star, just with the conjugates of the eigenvalues. So this is just diag lambda 1 bar through lambda n bar, like that. And now, of course, if I multiply these two matrices, we see that the matrix representation of T star T and the matrix representation of T star are equal to each other, right? And so therefore, the matrix of T star T with respect to this basis, phi 1 through phi n, is the matrix representation of T star T with respect to the basis, phi 1, phi n. And of course, what's it going to be? It's going to be the diagonal matrix. It'll just be equal to the diagonal matrix, lambda 1 bar squared, lambda n bar squared, like that, right? Okay, perfect. And that proves that T is normal, right? And so hence T is normal. Hence T star T is equal to T star, right, in this case. And so if you have an orthonormal basis of eigenvectors, then you're automatically normal. Now let's suppose that you're normal, right? If T is normal, then we can apply Schur's lemma. Schur's lemma asserts that there's a basis psi 1 through psi n hat, okay, such that the matrix representation of t with respect to this basis over here, psi 1 hat. And of course, this basis actually by Schur's theorem there's not uniqueness unless I put some extra conditions on it. This matrix over here is upper triangular. Okay. And so of course what that says that delta will be C11, C12, C1n, 0, C22, C2n, right? And then 0, 0, C33, C3n, and then lastly 0 all the way down to CNN. So that's what our matrix delta looks like. Now let's look at the norm of t of psi 1 hat squared. Well, let's just look at the norm of t of 1. What we're going to output over there? Well, if I input psi 1 into t, I'm just going to get C11. So if I do this thing over here squared, right, that'll just be C11 squared. But that has to be equal to the square of the adjoint by the fact that it's normal over here. So I'm using the normal assumption over here now to prove that. And what is that? Well, that's just going to be the conjugate transpose of this thing. So now I'm going to do all the columns. So I'm going to do a conjugate transpose of this. Then we're going to have C11, C12, C1n. This is going to be C11 squared down to C1n squared, right? But since those things are equal, I have C11 squared, C11 squared. That says all these terms over here, C2, C2n, C3n, C4n, Cnn, all the terms over here in that first row are going to be 0, right? That's excellent. So those are all 0, right? So now what can we say? Let's do the same thing over here. Let's look at the 2 factor now. So all those have turned into zeros, right? So let's say all those are 0. That's a 0. That's a 0. That's a 0. Now let's do the same thing with psi 2. I know that t psi 2 hat squared is just going to be C22 quantity squared. And the conjugate transpose has to be equal to the same thing as the norm of the conjugate transpose squared, which is C22 squared plus C23 squared plus C2n squared. And now since I have the C22 squared and the C22 squared, all those terms over there have to be 0, right? So in other words, all of these terms over here past the C2 have to be 0, like so. And then continuing in this fashion, so similarly, continuing in this fashion, we see that delta is really what? Is really C11, CNN, and then 0 everywhere else, right? So in other words, according to Schur's theorem, there's an upper triangular representation, but of course with respect to this basis psi 1 through psi n, that upper triangular matrix is actually a diagonal matrix, right? And so what does that say? That says, of course, that since you're unitarily equivalent to this upper triangular matrix, these numbers C11, C1n is the same thing as the eigenvalues of what? Is the eigenvalues of t, right? So in other words, the spectrum of t is just going to be what? It's going to be C11 through CNN, right? And what that proves that so if t is normal, then with respect to this basis, your diagonal set says all of these things are the eigenvalues. Psi 1 through psi n are the eigenvectors of t and their unit eigenvectors. And with respect to that basis, this matrix of t is diagonal, which shows that I have an orthonormal basis of eigenvectors of t in the case when I am normal, and that proves the complex spectral theorem. Thank you very much.